Inverter.
Welcome to clickmyproject.com.
Let's discuss about the product. Our product is analysis and design of a low voltage, low power double tail comparator. The need of the ultra low power area efficient and high speed analog to digital converter, that is ADC, is pushing towards the use of dynamic regenerative comparators to maximize speed, power efficiency and area efficiency. Here an analysis on the delay of the dynamic comparator will be presented and analytical expressions are derived. From the analytical expressions, designers can obtain an intuition about the main contributors to the comparator delay and fully explore the trade-off of the dynamic comparator design. Comparator is one of the fundamental building blocks in most ADC. Many high-speed ADCs such as class ADC require high-speed, low-power comparators with small chip area. High-speed comparators in ultra-deep 4 micrometer, that is UDSM, CMOS technology, suffers from low voltage supply, especially when considering the fact that threshold voltage of the device have not been scaled at the same pace as the supply voltage of the modern CMOS process. Hence, designing high-speed comparators is more challenging when the supply voltage is smaller. In other words, in a given technology, to achieve high-speed larger transistors are required to compensate the reduction of supply voltage. A new comparator, that is, in our proposed method, we have proposed a new dynamic comparator is presented, which does not require booster voltage or stacking of so many transistors. That means it produces less efficiency and less area efficiency and more power efficiency. Merely by adding a few minimum size transistors to the conventional double-tail dynamic comparator, latch delay time is profoundly reduced and we are getting a promising result. This modification also results in considerable power savings when compared to the conventional dynamic comparator and double-tail comparator. Many techniques such as the boosting methods, techniques employing body-driven transistors, current mode transition, and those using dual axis processes can handle higher supply voltages have been developed to meet the low voltage design challenges. Boosting and bootstrapping are two techniques based on augmentation the supply, reference or slack voltage to address input range and switching problems. The disadvantage on the other hand is the fact due to several stacked transistors, a sufficient high supply voltage is needed for a proper delay time in existing design. Another important drawback of this fixture is that there is only one current path via tail transistor. That's what we are going for, a double tail transistor. In our proposed transistor, we are having two tails. So the design, we are having two supply tails. Due to better performance of the double tail architecture in low voltage applications, the proposed comparator is designed based on the double tail structure. The main idea of the proposed comparator is to increase the efficiency and to reduce the area efficiency. And we are obtaining the latch generation speed. The operation of the proposed comparator is giving promising results. So finally, by the proposed method, we have measured leakage power, estimated area and number of transistors, supply voltage. Let's see the architecture design of our proposed double-tail comparator. Our comparator design is performed in Tanner tool because our comparator design is based on CMOS technology. Basically, for CMOS technology design, comparators, especially for comparator design in CMOS technology, the Tanner tool will give us better results. So the CMOS circuit is designed in Tanner. Before that, we are designing the architecture of normal comparator. That a normal comparator design is modified to double tail. That means we have to design that comparator for two power supplies. That means each one supply is connected with each tail. So we are having two tail and two supply voltages. The purpose of comparator is comparing of the inputs. While we are giving two inputs, it will compare the two inputs and finally it will identify the output which is highest output. So regarding to two inputs, it identifies the highest output and which provides the highest output as our result. So among the two inputs, that means we applied two supply voltages. So among the two supply voltages, the comparator identifies the highest supply voltage and the highest supply voltage is produced as our output of our comparator. So the comparator produces the output. Finally, we are getting the compared result. So by the compared result, we are analyzing the performance of the comparator through the speed and throughput, gain, and the delay time, power consumption. In lot of such ways, we are discussing and confessing about the product. This is the tool we are using for the simulation. This tool is called the Tanner tool. In Tanner tool, basically it has lot of sub devices. That means we are having SEDIC, WEDIC, LEDIC. Like this, we are having separated layout design for waveform designs and for circuit design. So similarly, we are having separate lines for design of separate parameters. So our CMOS design is performed in SEDIC. So our performed design produces the output in WEDIC. The T-space, that means we can export the code of the designed circuit in T-space. So we can work in the code in T-space and we can modify it as our requirement. So we are using SEDIC for the circuit design, T-edit for the extra modification, and WEDIC for the output design and analysis of the output waveform. So this is the tool we are using for here. By clicking this, we can start a new project. So to start every new project, we have to open a new cell. So by clicking the cell, we can design a new circuit design. So in the cell, we can include lot of libraries which consist of transistors, CMOS transistors, resistors, capacitance, such as general devices. So after we designing, we have to set the setup simulation. After that, we have to save the file and we have to execute it. So if we executed the circuit in correct manner, we can get the output in WEDIC.
Thank you.